Okay. Okay. Good afternoon. So last week, or last class actually, we look at the serviceability limit state conditions for the structures. Okay. So we will discuss a few questions how to find out the serviceability conditions, the deflections and cracks, and then we move to the ultimate next week. So before we start, the ultimate limit state. So when you look at this, the ultimate limit state in concrete, we work out two important things. One is the deflection, other one is crack. Okay. So if you look at the Australian standard AS 3600, all of you should have that standard with you. I think the first week I explained how to download the standards. Those standards are important. We will use that standard throughout this unit. So if you look at the standards, this is the AS3600. So you go to the so this is for the 8.5, section 8.5 is for deflection. The deflection of the beam, and 8.6 is the crack control. So we will see what standard says, and then we will look at the tutorial questions and how to find out each terms. So then you will have a clear idea what we need to do for the buildings or design of beams. The similar clauses are in the section 9. Section 9 is for the slab design. So the similar sections you can see deflection of slab, crack control. So both are very similar. So if you understand the beam, the deflection of the slab and crack control of the slab will be much easier. Okay. So here the deflection of the beam. So technically the Australian standard, as we discussed in the week 1, they put some limitations. Okay. The maximum deflection or maximum cracks and everything has been defined. So to find out the maximum deflections, you should be able to go in the early clauses. There is a closed deflection. Yes. So this is the deflection limits. So the standard define what is the maximum deflection that is allowed in the structures. Okay. So here you can see the deflection limit. The delta is the deflection. The L effective span, we will come to that one in a minute. So the delta upon span, deflection upon effective span is given here. That is a maximum value. Okay. So this is for the normal beams and slabs, and this is for the cantilever beams and the cantilever slabs. So that means cantilever means one end is supported, the opposite is free to move. So if you look at that one, they also say the total deflection, and sometimes they give it different things. Okay, so we need to know how to find out total deflection, and then we should be able to check with the limit. If it is satisfied, that's fine, otherwise we need to change it. So the limits are given in table 232. Then we should know how to find out total deflection, or how to find out the short-term deflection. Okay, so this is something very soon after the formwork is removed. So they give the limitation for different cases, so we should know how to find out deflections. Okay, so that is what we are going to learn here. So we'll go to the 8.5, section 8.5. In this section they talk about two methods. Here they talk about two methods under the deflection of beams. They use two methods. The first one is a simplified method. So this is the simplified calculation. Okay, so 853 is simplified calculation. Then under that one they talk about short-term deflection and the long-term deflection. So we'll come to that one in a minute. So they give the long-term deflection. And the second method is a deemed to confirm method, 854, deemed to confirm method. So we have two different methods. For deflection, we have two different methods. We have two methods. One is simplified method. Other one is deemed to confirm. So if you look at the standards compared to this one, the deemed to confirm, this is more accurate. Okay, this is more accurate compared to this one. So this is kind of a conservative approach. Okay, so they use some conservative approach to get the deflection. They use some conservative approach to get the deflection. So if you look at this one, this need less data, that need only the less. If you don't use the microphone, could you please mute your microphones? Please, those who are not using microphone, you can unmute and do that one. Otherwise, okay. So deemed to confirm, use a very less data, very less information, but it's very conservative. This one will give better prediction of deflection. So say for example, if you have actual deflection, so sorry, the deemed to confirm deflection, let's say this is about 5.2 millimeter, 5.2 millimeter, and this one will be maybe 5.1 millimeter. The actual one 5.08 millimeter, something like that. Okay, so the actual deflection may be a little bit less than the simplified and the calculated ones, but this one predicts more accurately compared to this one. So this one is quite conservative, but it is easy to calculate. So you should know both methods, because sometimes deemed to confirm method may not work, okay, because they have some simplification. If it is not satisfied, then you cannot use them. Okay, so we will look at the simplified method and the deemed to confirm method both. So the first, when you have a beam design, okay, beam or slab, whatever, so technically this is the dimensions. B and capital D is the overall depth, the small d is the effective depth. Okay, so if you have a beam, first when you design, you need to find out whether your beam is satisfied, because we need to calculate bending moment, deflection, shear force and everything. Okay, so that is our objective. So when you ask to design a beam, okay, or building, whatever, so you technically you will design one by one, slab design, beam design, columns. So when you are saying I'm designing a beam, what does that mean? You are checking whether your design satisfies all the requirements, or your beam comply with all the requirements given in AS3600. Yeah, AS3600 is the standard for concrete structure, so we make sure all the requirements set in the AS3600 is satisfied. So that means your beam should satisfy bending check, shear check, deflection, crackings and all other tests. Okay. So if you want to do all these checks, bending, shear, deflection, everything, you need to calculate what is the maximum bending moment, what is the maximum shear force, or what is the maximum deflection. Yeah, so the standard says maximum deflection is this much. So we need to check those maximum values against the limit set in the standards. So if you want to do that, you need the maximum deflection. Okay, if it is a deflection check, you need the maximum deflection. To calculate deflection or bending moment or shear force, whatever, what you need the loads. You need all the loads. You need the dead load, live load, wind load, whatever. So if you want to find out all the loads, the first one is the dead load, which is the permanent loads. One of the main component of the dead load is self-weight. So we need the self-weight to find out total load. Then you should be able to calculate bending moment, shear force, whatever you need. So if we want to find out the self-weight, we need the dimensions, the size of the beam. okay? Size of the beam, cross section of the beam. So we need those dimensions. So if we want the dimensions, technically we need to design that one. So we need to determine the size of the beam and the reinforcement details. That is called design. So but to get that one, we need the self-height. For the self-height, we need the dimensions. So it's like a egg and chicken story, okay? So we need to start somehow. So what we do is we will assume a thickness or size of the member and proceed. Okay? So if you ask to design a slab, you will start with 100 millimeter thickness or 200 millimeter thickness. So you will assume a thickness or size of the member and find out the self-height. Then you can find out total loads, and you can find out maximum bending, maximum shear, maximum deflection and everything. Then you can check it. So if that doesn't work, then you can change the dimensions and redo the calculation. So that is the design. But the question is how to reduce the trial and error. Yeah? How to guess good thickness or good size in the first instant. So for that, we will start with the deflection check. Okay. So what we do is we will assume a size or depth, whatever, and do the deflection check. So if the deflection check passes, if the thickness satisfied the deflection check, then you can say your structure or the assumed size most likely be okay with the other checks as well. So this is the first things we need to do. So once you assume the thickness, you need to do the deflection check. Okay, and that at this stage, if you assume the size, you don't know the reinforcement or anything. Okay, you don't know the reinforcement, AST or anything. So we need to use deemed to confirm method. Deemed to confirm method to check whether your assumption is correct. Okay, otherwise you need to change it. So for that we will look at how to do the deemed to confirm things. So the deemed to confirm method says L effective upon D should satisfy that the equation. Okay. So the right side they have the equation. So here the L effective, we have different spans. Okay, so careful, the notations should be checked carefully. L effective, so you go to the section 1.7. I will show that one quickly because these are very important. Many students don't care and they will end up with wrong answers. Section 1.7, you don't need to memorize anything, okay? So as long as you know you have to get these values, should be fine. Go to the L. So here they have a few different L's. So the first one is center to center. Okay, so I can't show both. So those who have the standard, just open this page I will explain that. Okay, so the first one is L, which is sender to sender. So if you have a column, and this is the column, so this is the column 1, column 2, and it will continue. So this is beam. Or it can be your beam and slab. Everything is same things. So this is your slab. This is the beam. Here this is beam. Okay. This is column. And this one is a beam. This is slab. So your structure looks like this. Okay. So this is your, in this case, for slab, beam is support. For beams, column is support. So the first span, they said sender to sender distance. So from here to there. So this one is called capital L. Okay, the sender to center. So that one here to there. This is L. Span. That is normal span we call. So that is here. They said sender to sender distance between flexural member. Okay. So the next one, the other one is a column. The L effective, LEF. Okay, LEF, and we need for that LN. So there is a one dimension called LN. LN is the clear distance. So LN means clear distance. This one. This is LN. Here. This is LN. Okay. That is a clear distance. So technically, LN is equal to L minus half the column 1 minus another half column 2. Okay, or it can be half beam 1, beam 2. Okay, so that is the clear span. And then they also have another one called L effective. If you look at the L effective, they say effective span. Okay, the effective span lesser of two things. So there should be minimum of Ln plus D or L. Ln plus D or L. So whichever smaller should be the effective span. So we have, these are three important L's, and they also have LOs and others, but we will look at this one. This is important. The center to center. Generally span means center to center distance. Clear span, effective span. So if you go to the section 8,
what is D?
oh, D is, oh sorry, D is the depth of this member.
Oh.
So here the full depth. Overall depth is a capital D. Okay, capital D. this one beam depth, here slab depth. Okay, so that is the depth. So once you have this one, you should be able to do the calculation. So the deemed to confirm method says L effective upon small d should be less than or equal to K1 delta upon L effective B effective EC K2 FD effective 1/3. So they said your L effective upon small d should be less than this value. So if you assume a depth capital D, so if it is a beam, technically you will assume an overall depth, and you want to see whether your assumption is correct. Okay, we need this process for the project. Okay, for your assignment you need all this discussion. So we assume this one. So I need to check whether that my assumption is correct. So for that I need the small d. So what I need is, we need to provide some reinforcement. I don't know how much, but definitely I know I need the reinforcement, and I also need the shear reinforcement. I need the shear reinforcement. So, sorry, this is not D, this is B, sorry. This is B. So the D is the centroid from here to there, that is D. Okay, this is B, sorry. The small d comes from here to the centroid of the reinforcement. So yesterday we look at this one. So small d is equal to, so this is capital D, we assume that one, minus cover minus diameter of the shear reinforcement. So from here to there, the diameter will come, and then half the diameter of main reinforcement or longitudinal reinforcement. So this is the equation for small d. Okay. For slab generally we don't provide shear reinforcement, so everything is same except this one. We don't have anything for the slab. Generally we don't need the shear reinforcement for slabs, so the small d calculation will be exactly the same. So we only have this part out. Okay, so that's the difference. Is it boring that lectures? Someone is sleeping. Okay. Are you okay? Are you okay or? So the small d, so we assume this one, we have to get this one, we have to get the cover. We have to get the cover. Section 4 AS3600. Yesterday we discussed this one.
Yeah.
So I saw the table and everything. So from the section 4, you should be able to get the minimum curve. So the diameters, you should put it generally, I think in the yesterday's in the slides, we put that one. So generally the N-type bar or R-type bars, N-type is the normal reinforcement, and this is plain steel. Okay, so N10 or N12 should be sufficient. N-type 10 millimeter bar or 12 millimeter bar should be enough. If it is very small shear forces, we might use R10 as well. R6, R10. Normally nowadays we use N-type. Okay, but if you do some lab work, this might be easier because this one is difficult to bend. Okay, so we use in the labs, we use R-type so that it's easy to bend the reinforcement. These are difficult. So what is the difference between N-type, R-type? So this is the normal reinforcement. FSY, the yield strength is 500 MPa. This is FSY, 250 MPa. So nowadays we use N-type. This one we will assume. So for slabs we use N10 or N12, but for beams, this is for slab. For beams, normally we use N16 or N20. It will go up to N40, 40 millimeter bars. Okay, yeah, 16 mil, 20, 24, 32, 36, 40. Okay, so we have different type of diameters. So you should able to assume I'm going to use this one. That should be okay. We don't know how many bars we require, but you should be able to put it, and you should be able to find out small d. And this one, where to get this value? You just look at that one, table 232, table 232, you should be able to get it. We have to get this value, clause 3.1, clause 3.1, there is a table for yesterday we discussed it. So you should be able to get EC value. B effective width of the beam okay, effective width. If you have a rectangular beam, that is same. If you have other shapes, they explain how to get it under the effective width of the beam. We will discuss that one when we study more about the T-beams. But at this stage, it is a width of the beam. So we have all the things except K1, K2, FD. So K1 is given here, and K2 also given here. So K2 is there. For simply supported beams, K2 is this one. For continuous beams where the longer span to shorter span ratio not exceed 1.2, then you should be able to use this value for the end span and interior spans. End spans are at the end, the interior spans are in the middle. But you need to make sure the adjacent span ratios are less than 1.2. If not, what do you need to do? The adjacent spans are more than 1.2, what you need to do? You can't use it. Okay, so in this case you need to go to the simplified method. Okay, so we need to get this one. So if you have a continuous span, so this is called end span. Both are end. But if you have large number of, this is end span, this also end span, these are interiors. Okay, interior spans. If you have, these are columns. So for end span they said 2.4 upon 384. For interiors 1.5 upon 384. This is the K2 value. Okay. So if I ask you to check the deflection, which span you will check? If I ask you to check whether your beam is okay, if I ask you to check whether your beam is okay, what you will do? Which span you will use? End span or interior span? You can do both, but if I ask you to check with only one span, which span you will select? Or in other words, which span will give larger deflection? Which span? Huh? End span will give larger deflection. Huh?
Interior span.
Interior.
Yeah.
Now the end span will give larger deflection. Do you know why? So generally when you have the deflections, this is rigid, yeah? So think of this one, okay? So generally you have, forget about the continuity, it is like this, yeah? Yeah, but it is continuous here, so you can't have the beams like this, isn't it? Yeah, so because if it is a, you can't have the beams like that, so what will happen? The deflected shape, because of the continuity, this is wrong, so this will goes like this, so the deflection will go like this. You can't have a sharp, you can't have sharp turning like this, right? Okay, so here you have in the interior span, you have this beam will make it up and this side also make it up, so your deflection will be smaller. But this side there is no continuity, only the rigid support, so this will be little bit larger than this one. Okay, so that is normal. It's a end span generally will give larger deflection. Similarly, the corner panel in the slabs will give larger deflection, the corner panel in the corners. So we will look at the K2 value. The K2 value is here. Then you will get the K1 value from this one. So generally you can assume we use very small 1% of steel initially. So then you should be able to get K1. The FT value given by two equations. This is for the total deflection and this is for the incremental. Soon after you remove the formwork, this will be the deflection. Remember in the table 232, sometimes they said total deflection, sometimes they said the deflection immediately after the removal of the formworks. Okay, so you should be able to check both the total deflection and the deflection soon after the removal of the formworks. So then you substitute, you calculate, you know the G value and the Q value. So you should be able to read these values, this C, the long-term factor, short-term factor, from the AS 1170 part 0. Okay, so if you want, I can show where to get AS 1170. Yeah, here they have the short-term factor, long-term factor, combination factor, everything is here. So for the type of the, depend on the type of the building, you should be able to get those factors. So you should be able to get, depend on the purpose of the building, you will get these values. At the moment, KCS, if you don't have the compression reinforcement, generally KCS you can use as a 2. They gave the equation here, but for the initial calculation use a 2, okay, because there is no compression reinforcement. So we'll talk about this one a little bit later. So KCS you can use as a 2, then substitute the values, you will get all the values and check whether the inequality is satisfied with your assumption. If not, you have to redo all the calculation. Okay, so that is deemed to confirm, but we also need to know how to get the simplified method. So simplified method says, so for example, if you are calculating using softwares, if you want to calculate, so if you have some complex structures, okay, and you try to get the analysis using softwares, then if you use the softwares, you may not calculate using deemed to confirm method, you might use the deflection from the software. So if you are using that one, so we should put, because we don't, some softwares you can put the reinforcement and everything, but some softwares they just take the cross section detail, they don't actually put the correct reinforcement and others. So in that case we use some simplified method. So here what they said is you need to use your theoretical calculation to find out deflection. So if you have simply supported, you have some equations. If it is a continuous, they use some equations. So you can use this theoretical deflection calculation, but you have to use some different things. Say for example, if you have simplified support and the loads are here, what is a deflection? What is a maximum deflection? 5 upon 384 W L to 4 on EI. Okay, so this is the theoretical value. Yeah. So this is the theoretical value. It can be obtained from any textbooks. For the continuous also you should be able to get it. So there are some textbook, structural analysis textbooks will give the deflection equations for different structures, or you can use the softwares. That's not a problem. But here they say the W is the design load. This is generally the design load. So serviceability limit state, yeah, because a deflection. So serviceability limit state, not 1.2 G plus 1.5 Q. It's a different serviceability limit state. L is the span. So what is the value for E and I? So E is the concrete one. They said in the standard, they explained what are the values should be used here. Okay, what are the values we should use here? So if you look at that one, so they said use the clause 312 for the concrete E value. Okay, they have an equation, or you can use the table, E value of the concrete. Okay, so that's quite straightforward, that there's an equation or the table. This is the more complicated one. They said you have to use effective I value. They said effective I value. Effective I value. So what is effective I? I is the second moment of area. Yeah, I is the second moment of area. So we need to find out I value. To find the I value, the effective I value, they gave this equation. Okay. So to find out the effective I value, effect is second moment of area. They gave this value. ICR 1 minus 1 minus they give this equation. Effective second moment of area is equal to ICR, that is a cracked section. So second moment of area for the cracked section, divided by 1 minus I cracked against the second moment of area of the cracked section, divided by uncracked section, then cracking moment divided by maximum moment. So this is the equation they gave. So I need to find out the cracked sections I value, uncracked section I value, the cracking moments and the maximum moment. Yeah. So to find out this one, we discussed the theoretical approach last class. So those who look at this one, so this is the cracked section and uncracked section I value. So this is the uncracked section, this is the uncracked section I value, and this is the cracked section I value. So to get this one, you need the reinforcement detail. So you can't do the simplified deflection calculation at the start. This can be done only after calculating all the reinforcements and everything. Okay, deemed to conform method, which I discussed earlier, is easier. Okay, you don't need the reinforcement details, you only need the depth, and you should be able to calculate or check using deemed to conform method. But simplified method requires more data. You need all the dimensions plus area of steel. If you don't know the area of steel, you cannot use the simplified method. Okay, so here I explained yesterday. So the equations are given. Okay, so I will quickly explain how to get that values, how to get the equations. So if you have a section this is uncracked section, so there is no cracks. So we have some steel, so I am going to analyze this one. I need to find out I value for the uncracked section, second moment of area for this section. So if you want to have the second moment of area, the whole cross section should be made of same material. You cannot use, say for example, second moment of area is this one. What is the second moment of area for the rectangular section? What is I value for the rectangular section about the centroidal axis?
BD cube by 2.
Huh? Sorry, I couldn't.
BD cube by 2.
BD
Cube by 2.
BD cube upon 2. 12. Yes. BD cube upon 12. Okay. So that is for the rectangular section. And we also need to know, so if you have this is centroidal axis, BD cube upon 12, and if I ask you to find out that I value about this one parallel, what to do? parallaxis theorem. So that is equal to centroidal I plus area times distance square. So that means BD cube upon 12 plus BD, area is BD H square. So this is, it is not concrete. It is not concrete. This is called parallaxis theorem. This is the strength of material. This is strength of material. We need those knowledge. So if we want to use here, I need the whole section is made of single material. Here we have, this is steel, and the rest of the part is concrete. So I am going to replace this steel section by concrete. I'm going to replace the concrete. Sorry, I'm going to replace the steel with the concrete. So the steel will take large force. So the E value larger than concrete. Yeah, the E value, this is around 200 gigapascal, and this is in the 32 gigapascal, something like that. Yeah, so we have large value for steel. So in terms of the stress strain relationship, for the same strain, concrete will take larger stress. The stress will be larger. Yeah, so that means it will take more force. Yeah, for the same strain, the steel will take more force. So what I am going to do, I am going to replace, please understand, I am going to replace the steel with the concrete. So if I want to replace this one using equivalent area, I need more concrete because steel can take larger force. Yeah, so I need to have the equivalent area, I need more concrete. So that how much I need, so that is equal to, based on this ratio, okay, based on this ratio, so we need N times, this is the area of steel, this much of concrete to replace the AST. AST is the area of steel. I need this much of concrete, I need this much of concrete to replace the steel. N is the ratio between the elastic modulus of steel and concrete. So I am going to replace, so I remove the steel out, I will remove the steel out, the same place I need to put it. Okay, so in this line I should put it. So I remove the steel out, so what will happen? There will be some holes. Yeah, when you take that steel out, that place need to be filled because this is uncracked section, the whole beam is there. So there is hole, so there are 3 holes because I remove the steel. So first I need to fill that hole using some of the concrete here. Okay, so the AST amount of concrete will go here to fill that holes, and then we have n minus 1 AST, because 1 AST goes here to fill the holes. So the rest of the concrete should be put here because there is no other place. So the total area of this one, total area of the shaded part is n minus 1 AST, because one part went to here, so that is full beam. You understand? Yeah. So now the whole section is made of concrete, but it is not rectangular section anymore. We have something here. So as you know, if you don't have this one, this is a rectangular section, this is a rectangular section, so the centroid will be in the middle. Okay, centroid will be in the middle, so that is for the rectangle. Yeah, but we have some additional area here, so my centroid will move here. So this is the new centroid, so this is the new centroidal axis. So this is the neutral axis, because according to elastic theories, for the elastic material, the neutral axis will pass through the centroid. So centroid is here. This centroid, for the rectangle, we have the new centroid because we have additional areas. So I need to find out where the centroid is. Where the centroid is, because it's moved downward. So I need to find out y bar. Okay, so this is the old, this is the neutral axis for the rectangle. Okay, so that is, I put this as a capital D. So this is D by 2. Earlier the whole thing is D. If you don't have these two areas, the centroid will be here. Now we put some additional area at the depth of small d. This is small d, effective depth. So we put some additional area, so that will move downward. So I need to find out that. So what is the method? So as you did in the second year, finding centroid. So area and put section, area, y bar, a y bar. Yeah, you remember this one? So first we will look at the rectangular section. So this is B. So section, rectangular section, and the additional section. So the area of the rectangular section is B, capital D. The centroid from here to there, this is the centroid, D by 2. The additional area is here, so that area is n minus 1 AST. The distance from here to there is small d. So this one b d d by 2 n minus 1 est d. So I will add this part bd plus n minus 1 ast. So then you can add this one as well. Okay, so what is the y bar? Sum of a y bar divided by sum of a. So this is very basic, normally you covered in the second year, isn't it? Yeah. And you should be able to find out that value. Okay, so here I took the moment from the, I take the a y bar everything from here. Okay, I take from here. You can take from any point, doesn't matter. Okay, so in this one, the document, I take the moment about, so here I took the moment about the neutral axis. So don't confuse, it looks different but you will get the same answer. So I took the, in that PowerPoint I take from here, so all the distance measured from here, so that means this one is this distance, like that. Okay, so everything is measured from the neutral axis, from this line. But in these workings I work out from here, so every distance are measured from here, so both will give the same answer. Okay, so the approach might be different, you get the same answer. So you should be able to get the centroid where it is, either using that method or this one. So then you need the I values, second moment of area, second moment of area. So I need to find out the second moment of area about this axis. Okay, I need to find out the second moment of area about this axis. So in this case we have this area plus this area. Okay, this area plus this one. So first we will work out this one. For this area about this axis, about the centroidal axis, BD cube upon 12. Okay, so I will write that one, BD cube upon 12. So this one is about this axis, about the centroidal axis. Then I transfer that one here, I transfer that one here. So area times plus area times this one, I'm using this centroidal axis plus area times distance square. Area times the distance, this is y bar, this is d by 2, so this one y bar minus square. Okay, plus, so this one is just an area, so second moment of area is equal to area times distance square, area times distance square. Area is n minus 1, area times distance from here to there, from here to there. So this is small d, this is y bar, so the distance is d minus y bar whole thing square. So this is the second moment of area. So this is the second moment of area. Uncracked section. Okay. So in the assignments, if anything comes, you may able to use the equations given in the lecture slides, but you should be able to derive if someone asks. Okay, you should have clear idea. You are doing masters. Okay. So you mostly know the concrete design already, from the undergraduate. So I'm not expecting, I will not ask in the exam to derive this one, okay? But you should be able to get this one. So similarly for uncracked section, the only difference is we don't have anything in the bottom part. So you should be able to find out the centroid using this equation, the first one, and the second moment of area of the cracked section is given there. Okay, so b y bar cube upon 3 times n est d minus y bar square. I put y bar c here. Earlier y bar UC, uncracked UC, and C cracked, so that it will not confuse. Otherwise everything is a y bar technical. Okay, so you should know, because for the simplified method, we need ICR, which you have, capital I, uncracked section and cracked section, you should be able to find out. Okay, the maximum bending moment, when you draw the bending moment diagram, you should be able to get the maximum bending, which is m star, and then you should be able to, this is m star, this is the cracking moment. They gave the equation here. The cracking moment is given here. So at the moment we are not studying the pre-stress. So this will be 0. So don't worry about this. P upon AG is 0, and PE also 0. So the P is 0 because we don't have pre-stress. But if you have pre-stress, that will come after the break. We need this one and that one. Capital P is the pre-stress force. We are not using that one. So we need to find out the F dash C minus sigma CS, which we discussed yesterday. Remember?
Yeah.
This is the flexural strength of the concrete, and this is the shrinkage stress. So they gave the shrinkage stress using this equation. So everything, this you should be able to find out. They gave the equations. That's not a. So here you need to find out shrinkage strain. You should find. So we discussed that one yesterday, how to find out shrinkage strain. There are two types of shrinkage strain. One is chemical shrinkage, other one is drying shrinkage. So you should be able to find out and substitute. So again, the P is the pre-stress. If you are not sure, refer the notations, section 1.7. Okay, So the P is the pre-stress, so this should be 0. We don't have any pre-stressing steel, pre-stressing force, so these things are 0 at the moment until week 7. We have that one in the latter part of this unit. So at this stage, the AST upon BD is the PW, and ASC is the compression reinforcement. Again, we don't use the compression reinforcement normally, that is 0. So then you should be able to find out the cracking moment. So that cracking moment, technically in actual case, when the crack will develop. Okay, so when the crack will develop, so you should be able to find out so what is the Z value? Section modulus of uncracked section. How to find out the Z value? Anyone? What is section modulus?
Simply I over Y, sir.
I upon Y, yeah. So for uncracked section, you know that what is the I value? Yeah?
Yeah.
And they said refer to the extreme fiber. So you have this is the uncracked section. The extreme fiber will be here. Extreme fiber will be here. So Z is equal to I value, that is here, you already have. Okay. So Z is equal to I divided by the extreme fiber is here, so the Y measured from the neutral axis, this one. So divide by T minus Y bar. So this is I value, sorry, Z value, I, the uncracked section, divided by D minus Y bar. So you should be able to calculate this one. Okay. So with the full numbers, the solutions are given. Okay. The full solutions are given with all the numbers. So then this is the deflection, okay, short term total deflection and the deemed to confirm. So everything is explained. Then you should be able to read the standards and get the values and work out. And full workings are there. And if you have any difficulties, please ask me. So that's what I put the solution earlier. So you should be able to work out. Don't read the solution as it is. Okay, this is not a storybook. You need to work out. Unless you work out, you will not learn anything. Okay, so solutions are given as a guide, so you can see, okay, so he got this value, where to get this one. So I need to find out deflection. So the question 2 is actually deflection. So then the loads are given. For short term, and the loads is different, because this is for the short term load combination, the long term load combination. All others are same. The short term generally they said 52 days, the long term they said 30 years they said. So generally you should be able to look at and the full workings. Generally that shrinkage calculation will be different. Okay, all others are remain same. So you can see the shrinkage calculation changed, and then it will change the deflection calculation. Okay, so please look at the deflection section. The study guide is given, isn't it? There's a study guide. Have you seen that one? Is it given, isn't it, or not? Do you have access, isn't it? How many of you look at the study guide? No? This will fly, okay. If I don't put it, just let me know, because I have a couple of different units. Just explain step by steps. This is explain the theory and what is the shrinkage things, how to get these values, okay, where to get that values, everything, and creep, RC structures under this one, so uncrack section, crack section, so the cracking things. So this is the cracking moment. P is the free stress force, which is 0. Everything is explained. Almost the study guide will give the crackings, how to find out that one. And we have example, full worked example that is different from the tutorial question, and we explain step by step where to get, how to get that one. Yeah, and the crack with calculation, how to do the crack with calculation. So this is 1 week. Okay. So next week we'll have another study guide like this. So if you leave it, it will be pile up. Okay, it's a double credit unit, isn't it? So generally it's a 25 hours, they say.
Yeah.
This one and another unit you are studying 2 units only, isn't it? Full time. So undergraduate students study 4 units.
4/7.
4 units. This one is equal to 2 units technically.
Oh.
So that's why is most things comes very quickly. Okay. But is assignments and exams not very difficult, but you need to know these things, otherwise you can't do any concrete. I can cut easily, I can skip this one or do this one in nice simple things. I can teach you very nice things without showing all this one. But when you go to the industry, you will understand you don't know anything about the science. That's all. Okay. So the assignments, that's what we have a drop-in session. I will explain what to do. So you start. So this one explains step by step. You can see that how to get this one, where to get everything step by step. Okay, so please read this one. And when it is says, so equation given in 853, find out that equation. You don't need to prove anything. So here, even though we explain how to get these things, technically you should be able to use it. So they say this one, so TH is where to get this one, and then substitute, that's all. So as long as you should be able to use the equation should be okay for this design. So the how to get these equations and everything, so for example the crack section, how to find out I value, how to find out the centroid, I explained how to get it. But technically if you know, okay, this is the equation for one crack section, I value, so this is the crack section I value, that's enough. You should be able to use that one. You don't need to prove that equation at all, okay? But you need to know where to get that one and what is each term means. So for that you need to read them. Is it clear? Study guide, basically what we discussed today is there in written form. Okay, so the next one is the crack things. Crack control is the other one. The deflection we can check using simplified or deemed to control one. The crack control, they have 3 different methods. Okay, we have 3 different crack control mechanism or recognition here in AS3600. You can satisfy the crack requirements using 3 checks, one of them. You don't need to do all 3. You can do one of that, but sometimes you cannot use all 3 in a given case because it's have some conditions. So here the first one is quite easy, that is here, that is a paragraph, but that is quite easier compared to all other things. So here you need to look at this one. For regions of beam fully enclosed building within the inside the buildings, then you need to satisfy these 2. Okay, so that means if you are designing something enclosed building and your member or beam will not expose to the environment, okay, then your crack control will be satisfied if you satisfy A and B. Okay, so that means the first one says minimum reinforcement should be placed in the tensile zone. So we will discuss this one in the next week under the bending check. So that's generally when you provide the reinforcement, so automatically that will be satisfied. Minimum area of reinforcement according to clause 8161. So that's definitely will be happen. And then the distance from the site of the beam to the centroid of the nearest longitudinal should not exceed 100 millimeter. So the distance from the site of the beam to the nearest bar should not go more than 100 millimeter. Okay, and the distance between the bars should not exceed 300. So the crack control, they said if you have these bars, okay, so they said from here to there should not exceed 100, or this one should not exceed 100. from the edge of the concrete beam to the nearest steel bar, centroid should not exceed 100. That is the first condition. So that means it should be less than 100. And this one less than 300. The spacing between two bars should not exceed 300, and it should not place far from the edge of the beam. That is quite straightforward and easy. So the first one, if the beam or slab is inside the building, is not exposed to the environment, it is easier. But unfortunately not all beams and slabs are inside the building. So in that case we need to use, there are two methods. One is a direct method and other one is an indirect method. Okay, so this is the indirect method, and the other one is a direct method, actually calculating this is the direct method, calculation of the crack width. Okay, so the calculation of the crack width, so technically you calculate the crack width, actually what is the maximum crack width, that should be less than particular values. Otherwise that is a direct calculation, quite lengthy. Okay, because you need to calculate this one and each of that. But the indirect method, here you need to check the maximum stress in the tensile zone bars. Okay, so we need to find out what is the maximum steel stress. So then if the steel stress is 180 MPa, and if that maximum stress is less than the value here, then your crack check is satisfied. So if you calculate the maximum stress of the steel, then you should be able to check using this table, and if it is less than this allowable limit, then that is okay. So this is a crack width of 0.2, this is crack width of 0.3, this is crack width of 0.4. So what is allowable crack width? Okay, for the normal case, if it is a reinforcement, some water retaining structure, we need the smaller crack width. Okay, but normal beams we can allow a little bit more. So that also so this is the maximum allowable crack widths for different situation. If it is a water retaining structure, it should be less than 0.1 millimeter. Okay, so it depends on the normal cases, or so that gives in the ACI standard. So this is the maximum allowable crack width. So if we calculate the crack width, it should be less than this one. Or direct method, calculating crack width, wait, I'll show that one, give me a second. So we need to find out. So we need to find out the maximum steel stress. So if you have if you look at the crack section, they said the maximum steel in the crack section. So look at the crack section, we have steel bars and we know the bending moment, the service bending moment. M star. So we apply the bending moment. So I need to find out what is the stress here. What is the stress here? So we allow some crackings because maximum crack width is given. So we allow some cracking. So we look at the cracked section. So if it is a cracked section, the beam is here. The rest of the part, this is the neutral axis down, is a cracked. So if it is a cracked, here compression, all the tensile concrete has gone, and we have the steel part. I replace the steel with the concrete. This is NAST, so this is the cracked section. Okay, this is cracked section. So this is everything made of, this is everything made of concrete. So I need to find out the stress here, yeah. I need to find out the stress at the steel. So that means stress at this point. But when you calculate the stress at this point, it will give the stress at this point when it is made of concrete. When it is made of concrete. So the stress in the steel in times, that is the ratio of the concrete. Stress when you have bending moment, M upon I, Y. This is the strength of material equation, M upon I, Y. Stress equal to M upon Y, I. This is the cracked section. Y is the distance from here to there. This is Y bar of the crack section, Y bar of the crack section, and that is D. So D minus Y bar. So this will give the stress in, ES. So you know what is the maximum bending moment under the service load. You can calculate bending moment using bending moment diagram. You should be able to calculate maximum bending moment. I crack, we already calculated. D, we know. Y bar of the crack section, I already calculated. So you should be able to calculate the maximum stress in the steel, maximum stress in the steel. So if this value is less than, the allowable stresses for 0.2 millimeter crack width or 0.3 millimeter, whatever, you your crack check is satisfied. So you don't need to do any more calculation. This is indirect method. Other one is a direct method, calculating the strains and find out all the things. Everything is here. Okay, but it's quite lengthy calculation. Even I work out the full workings in the tutorials as well as in the study guide. Okay, so we need to know there are 3 methods for the crack check, 2 methods for the deflection check. The deemed to confirm method is easier. For deflection, simplified calculation is accurate but is lengthy. For cracks, we have 3. The first one is enclosed building, is quite easier, quite straightforward. Another one is indirect method, finding maximum stress in the steel. And if it is less than the allowable stress given in the tables, that's done. The third method is a calculation of the actual crack width, that is using 8623, this one. So we need to do, we can confirm our design is okay using any of the method as long as it's satisfied. Okay? Any questions? It will cut out in less than 1 minute. Anyone have questions? Otherwise you can ask at 5 o'clock as well. In 1 hour we have another session. Okay? So we will see you in 1 hour. And we will talk about the project, what you need to do. And if you need to change any groups, we will talk as well. Is that okay? So only that this part is a little bit more calculation, so others are a little bit easier.
Too much calculation.
Their design is like that.
Yeah, but maybe I think in really